Hello. In this video, we will study the properties of exponential response. Okay, so properties of exponential response. So in source free RL circuit, we have seen that the I of t current will have this form, that is I naught e power minus t r by L or r by L into t, where this I naught is what? I naught is the current at t equal to 0, initial value. So this I naught is nothing but initial value of the current. Okay, so this is how the current changes in an inductor. Okay, now if you want to see the normalized value, that means if I divide by this I naught, then it will be minus r by L into t. So what is the maximum value it can have? It can have maximum value 1, because at t equal to 0, the initial current is what it is having is I naught, that is the maximum value. So that I am dividing by I naught. So maximum value left hand side it can have 1. Okay, so I of t by I naught equal to minus r by L t. So it is, if you plot this one, so this value if I take, this value will be I of t by I naught, and that value you can have maximum 1, because at t equal to 0 I of t will be I naught. So that will be having, and exponentially it is decaying. Okay, now if you calculate initial rate of decay, so we will calculate initial rate of decay, initial rate of decay, that is d by dt of I of t by I naught. This if we calculate, so if you differentiate, it will be minus r by L and e power minus r by L t. And at t, this is the rate of decay, but we want to calculate at t equal to 0. At t equal to 0 you would like to calculate. So at t equal to 0, if you substitute t equal to 0 in this case, what you will get? You will get minus r by L. So this is initial decay, that slope is minus r by L. Initial decay is minus r by L. Now we will define a time constant tau. We will define a tau, and definition is like this. If this, we will assume, if this constant rate of decay is assumed, constant rate of decay is assumed, then time taken for I of t divided by I naught to drop from unity to 0, then the time, if this constant rate of decay is assumed, then the time taken for I of t divided by I naught to drop from unity to 0 is called time constant or time constant tau. So what is the significance of this? So suppose actually the inductor current is exponentially decaying with an initial rate of decay is minus R by L. Now what we will do, initially suppose we will assume the initial rate of decay minus R by L will continue. It will not decay exponentially. Suppose if minus R by L, the initial rate of decay continues, so then the time where it reaches zero value, where the current reaches zero value, so that time is called tau or time constant. I will repeat, if initial rate of decay, that is minus R by L, continues, if it is assumed that inductor current will decay at this rate, then the time taken by the inductor to reach zero value, to reach the current, zero current, so that time is nothing but tau, or we will call it as a time constant. Now we will calculate what is this time constant. So initial value is 1 and it is taking tau time to reach 0. So I can write this equation, 1 minus R by L tau, initial value is 1, then rate of decay is minus R by L. At what time? After tau time it will be 0. Initially 1, after tau time, because of this decay, output will be 0 or final current will be 0. So then if you calculate this tau, tau is nothing but L by R. L by R. It is called time constant. Time constant. Now what is the significance of this time constant? If we write that at t equal to tau time, what is the I of t divided by I naught? I of t divided by I naught will be e power, we will substitute that equation. What is that? E power minus R by L t. E power minus R by L t. In this you have to substitute t equal to tau. So that is I of tau is I naught, I will take, or let it be here, I naught e power minus R by L tau. So what is this value? Tau value we have, it is L by R. So if you substitute that, you will get e power minus 1. So at t equal to tau, I of tau is nothing but I naught into e power minus 1. So what does it mean? We have calculated a time constant tau by assuming that if initial rate of decay continues, current will reach 0 after tau time. Now we will come back to this original equation and we will substitute this time constant in that original equation. What is the original equation? Original equation is I of t divided by I naught into e power minus R by L t. In this we will substitute that tau. So what we found now, after tau time, actually what will be the, if initial decay rate of decay is assumed, that is minus R by L assumed, after tau time it will reach 0, but it will not happen actually how it is decaying, exponentially it is decaying. So if you substitute this value in that main equation, we will find that at t equal to tau, I of tau or the inductor current will be I naught into e power minus 1. So this if you calculate, so what is the value of this one? So e power minus 1, that is 0.3679 I0. So that meaning after tau amount of time, actual value, if you if you take this one, this will be around 36%, 36.79% of I naught. So this will be at this 36.79% of I of t, or 36% of this one, I of t divided by I naught. 36% you will get. You can see here, if you take this one, 36% of this. So 2 time constant you will take. This is a 1 time constant. So after 1 time constant, the current reduced to 36%, from 100% to 36% it reduced in 1 time constant itself. Now if we consider a time constant, another time constant if we consider, that is after 2 tau, at t equal to 2 tau, if you consider I of tau, or I can even calculate I of tau by I naught, as normalized value also I can calculate. That will be I naught into e power 2 tau. 2 tau it will be minus 2, e power minus 2. So e power minus 2, again normalized value only if you want, it is I of t divided by I naught. It will be e power minus 2. That value will be 2 tau, 13.53%. So after 2 tau, 2 tau if you take, the value will be 13%, 13.53%. And similarly we can calculate after 3 tau, the output current will be 4.9% of the initial. Initially if it were 100 ampere, after 3 tau it will be 4.9 ampere, 4.9% of the original value. And after 4 tau the value will be 1.8%. And after 5 tau, so this will be 0.6%. So what we can tell, after 5 time constant, inductor current will be almost equal to 0. It's a 0.6%. 0 it will reach at t equal to infinity, but we can tell after 5 time constants, the inductor current is almost equal to 0. So this is the significance of tau, and how we derive, and what is the value for tau in the RLK, in the R source free RL. It is tau is nothing but L by R. Okay. Yes.